2021 question number 5. This is a big organic synthesis question. So we start with, the overall purpose of the question is to do the synthesis of this hydroxychloroquine. And we start with a simple IUPAC name of this ketone. So we're going to give priority to the ketone, so we're going to number the carbons 1, 2, 3, 4, 5. So it's going to be 5-chloro pentan 2-one. Just nice, straightforward naming question there. So 5-chloro pentan 2-one to start with. Then we have to draw the structures of B and C. So we go from this ketone to this, what would that be? That's like a diamine, 2 amine groups here. So we're going to react, so 2 things are going to happen, obviously. There's going to be chemistry at the 5-carbon, where the chlorine is, and chemistry at the 2-carbon, where the carbonyl is. So it's just a case of deciding, which step does what. So the idea here is you want to try and identify which part of this molecule relates to this molecule and this molecule. And it should be clear that I've got nitrogen here, nitrogen, carbon, carbon, oxygen. And that's going to be nitrogen, carbon, carbon, oxygen. So this is going to add on, and it's going to add on at the 5-carbon. Okay, so I'm still going to have I've got my 1, 2, 3, 4, 5 carbon chain, but then I'm replacing the chlorine with this, because you see also I've got the ethyl group over here, So it's just a straight swap for this molecule of the nitrogen onto the 5-carbon, removing the chlorine. That's just a simple substitution reaction. Alright, so nothing too tricky there. So it's going to be all this side of the molecule stays the same to here, and then instead of the chlorine, I'm going to have now the nitrogen with the other 2 groups on. So it doesn't matter how you draw that. OH, as long as you draw it correctly, that's the main thing. So that's fine. Then we do the ammonia step. So now we need to be turning this part of the molecule into something else. Now this is a little bit tricky because ammonia plus a ketone gives you a imine. Okay, so ammonia plus ketone gives you an imine, and an imine is your C double bond N with other stuff on it, obviously, rather than a cyanide. Okay, so what it's going to do is it's going to give us, it's basically just substituting out the oxygen for a nitrogen, like that. 1, 2, 3, 4, 1, 2, 3, 4, okay, like that. Now it's probably just worth knowing, and then obviously you need to have your 2 hydrogens on there. It's probably just worth knowing that that's a reaction that can happen. You can sort of work it out by thinking, well, like, what's going to happen is my ammonia is going to come in and do the attack here. Obviously there'll be some, protonation and that kind of thing, but you're going to end up, after a few steps, with something like an NH2 here and an OH here, and the point is that then this comes down and forms the double bond between the carbon and the nitrogen. I don't want to, you can look that up yourself if you're interested in that reaction mechanism. That's just a brief overview. And then this is obviously not our final product. Our final product is we need to change the double bond into a single bond. That's the only difference between here and here. Yeah. So this carbon here in my C is this carbon down here, and then this carbon is this carbon, and then I've got the nitrogen. So the only thing, this can't be right. I can't have 4 bonds to my nitrogen and it not have a positive charge. So that has to be just NH. So what I'm going to do is I'm going to put a hydrogen here and a hydrogen here, which is why this then becomes NH2. So hydrogenation. So there you have all your different things that you can do stuff with, and that is the one that's going to do the hydrogenation, which should be fairly obvious. Okay, so then we carry on. So what we've done is we've made this, which is this part of the final product that we want. So now we need to make this part up here, and that's what we do down here. So this is the synthetic route to go from benzene to our complicated looking thing here, and we want to draw the structures of D, E and F. This step here, that's the free mark that you get, because you should know that nitric acid and sulfuric acid react as a nitration, so you're adding the NO2 plus electrophile to the benzene ring, so you form nitrobenzene. Okay, so we all know that by now. Then I do this chlorination step with my Friedel Crafts catalyst here. So if I look at my final product, I can see that I've got my benzene ring and I've got a nitrogen here. So that nitrogen is going to be this nitrogen on here. So I go 2 carbons away. That'd be the meta position, ortho, meta. I've briefly forgotten my benzene naming convention. Okay, look, it's just 2 carbons away on the chlorine there. So it stands to reason that this step is just going to be putting on the chlorine there, which is fine. Then I have this reduction. So this is the similar to what I saw up here. Yeah, I've got my hydrogen with my catalyst. I guess at this point you just got to look and think about this and see, well, what's going to be reduced here. Definitely not the benzene ring. You're not going to reduce the benzene ring. That's not going to change, so something has to happen to this, and you'll see that here there's no oxygen bonded to my nitrogen. So this reduction step is, again, you should know, because it's very common. If you want to turn the benzene ring, just a standard benzene ring, into a benzene ring with an amine attached to it, you do the nitration first with NO2, and then you reduce it down. So you just get that. And I think that's probably going to be as easy as it gets for organic synthesis. You know, those are 3 very, very doable organic synthesis questions. Then it starts to get a little bit more tricky. So we go to reagent Z. Now it's important for us to remember what reagent Z is. So here, what I've got F, and I'm going to draw it out again. So F is my this thing, and then I'm going to add reagent Z, and I'm going to make this. So in other words, reagent Z needs to be this thing here. Okay, so that's what I'm making now. So reagent Z is synthesized as shown below. When treated with a base, diethyl malonate forms anion V-. So this is diethyl malonate. I add a base and I get an anion. And then when treated with an acid triethyl orthoformate, so that's this funny looking thing here, I react that with an acid and I get a cation. Then it fragments by losing ethanol to another cation, and then these two react to make that, and then I lose another alcohol to make my final product. Okay, so complicated. All right, now this is where it starts to get tricky. So what I find useful here is if I can just have in mind something, I don't know exactly what Z is, but I know it's going to be something along these lines. And this here, this has just got an amine. This carbon here is not part of F. So this carbon here has to be part of Z. So there's going to be a carbon there. And then, no, I'm probably okay. Let's leave it there for now. Right. So what I try to do when I go through these questions is, obviously I've done these questions before, so I know what the answer is. But I try to replicate as much as possible the thinking process that you would go through in the test. So I try to replicate the thinking process that I went through when I did the question. Otherwise, you know, if I could obviously just say, well, if you react this with a base, you get this, and draw it out. But that's not really helpful for you when you're trying to work out how you would approach this in an exam. So when we look at the base, what does the base do to this? Well, it obviously is going to be deprotonating it. Now, it could be, you know, anything. You've got to think about what kind of things could happen to this. I've got these two esters. Whenever I see an ester, I always think, okay, maybe I'm getting some sort of ester hydrolysis. But in this case, this is why it's so important to have this idea. Remember, this isn't what Z is. This is just my idea of what Z is almost like. And you can see that nothing changes between this molecule and this molecule except for in this position. That's the only place that I'm doing any chemistry. The rest of the molecule stays the same. So it is likely that when I form this anion, all I am doing is just deprotonating this carbon here. And that makes sense because the fact that this carbon is adjacent to two carbonyls means that the negative charge can delocalize. So these are very slightly acidic protons because that negative charge is able to delocalize. So anion V minus, I am now fairly confident, is going to be this. With the negative charge there. Okay. Great. And then that's why there's only one step here, because then what happens is I make the cation and the cation just comes in and attaches itself to here. All right. So we should now try and work out what that cation is. So I add an acid and make a cation. So all I'm going to do is just protonate this somewhere. Now this is completely symmetrical, right? Each of three of these arms coming off is the same. And when I protonate it, I'm obviously going to protonate it on the oxygen. So all I'm going to do is just add a hydrogen. Like that. That's the only thing that can possibly happen here. So I can now go ahead and write that one in. Try not to mess it up. And then I've got ethyl groups coming off each of these. And it doesn't matter which one you do, like I said. So I get that. Okay. So that's fine. Then I lose the alcohol. Now at this point, that should now be fairly clear what's going to happen, because what's going to happen is this is going to come off. And if I do that, here I've got my CH3, CH2OH, so I'm just going to be left with this, and now that has got the positive charge. Okay. So that gives me cation X plus, fantastic. And now those two can react together. So V minus and X plus react together. So here's my V minus. Here it is here. Try and get them on the same page. Here's my V minus. Here's my X plus. And like I said before, it's just going to be simply that this negative charge, where the carbon where the negative charge is, bonds to the carbon where the positive charge is. And that's going to be really good because remember, I did say, and it's a lot to keep in mind, but I did say that I need to have a carbon here in my Z, right? So that's good because this carbon in my final product is going to be this carbon here. Okay, so let's do intermediate Y, which is just, they give us less space for this one than they did for the last one. Interesting. So I have this, and then it comes down, and now I've got this. So I'm going to have O, O, like that. Okay, then I go from Y, this, oh, drawn it, looks like a man, excellent, with his arms outstretched. And then I take off another alcohol. So I know that this alcohol cannot come from either of these arms. It has to come from one of the legs. Okay, because this needs to remain intact. So what I'm going to do is I'm going to take off this. Okay, so I'm going to get like that, which, you know, I said earlier on that this is what I needed to get for Z, and I've got pretty much that, and the only thing I was unsure about is what this final thing here was going to look like, and it looks like this. However, when I've removed this, all I've really taken off is C2H5O minus. So I need to take off the other hydrogen. So this has got a hydrogen. Let me think now. How does this work? So this has got a hydrogen here, and this has now got two hydrogens here. I can't have that. And if I now look ahead, or if I look back to reagent Z, I can see that I've got a double bond here. Okay, so what I can do is I can work back from that double bond and know that there must be a double bond there. And then that means that I've got one hydrogen here, and I've still got one hydrogen here, and I've taken off the ethanoate, and the other hydrogen comes from this hydrogen up here, which is also lost. That's sort of like an elimination reaction. Yeah. Okay, alright, so let's carry on. So I feel like all of those 5 marks here, the 3 marks for the first step, those are all easy. V minus I think is fine. W plus I think is fine. X plus is fine. Y is fine. That one is tricky. People are gonna miss the double bond. And there's not really much we can do about that, except you should look at the final product and you should see that there's a double bond in the final product. Then, this is where the question really picks up in difficulty. I think if you're getting most of W, X, Y, and Z, or part of it, you're looking at getting gold. All right. But now, once we get into G, H, I, J, these 7 marks, these are really pretty tricky. And this is where you're looking for a high gold, maybe round 2, that kind of performance. When I did this, I found this quite tricky. So, again, I could just tell you what this reaction is, and I could just show you, talk you through every step in the reaction, but you can just look that up yourself. I'll tell you, this cyclization reaction here, this is called a Gould-Jacobs reaction. Okay, now, the chances that you have looked this up and learnt it before coming into the Olympiad is very, very slight. So what I want to do is I want to go through how you would approach this, not having seen this reaction before. So, the cyclization, let's not worry about the cyclization for now. I want to talk about that separately. Let's try and work backwards. So we see that I'm going to bring in the molecule that I made at the start, and I'm going to add it to this double ring system here. And you can see that what's going to happen is it's going to bond through this amine group here. So it seems likely that what I can do is I can just break off here and go backwards. And if I do that, I know that it's going to be like that. And then there has to be something here that directs the chemistry. So there has to be a group here that this is going to substitute with. So the only thing that I need to work out for J is what is it that's here instead of this molecule. Now, in order to get to J, the last step is POCl3. Now, I was a bit hesitant because, you know, my first thought is, well, look, it's got chlorine in it. Okay, so chlorine. All right, and I know chlorine's a good leaving group. I can imagine that the amine is going to come in and it's going to substitute with the chlorine. That would just make sense to me. But I was just not sure that POCl3 would do that. You know, it's not something that I have enough confidence with. But at this point, I think we can just use our common sense and we can say, look, you know, what I know that it has to be here, and then there has to be something that's going to replace. It makes sense for it to be chlorine. So at this point, I feel confident enough to just go in and say, all right, that's what J is. Now, the one problem I have with that is, well, if that's going to replace, you know, if this molecule comes in and reacts here, why doesn't it come in and react here? That is a question that is a little bit too complicated for now, so I'm not going to worry too much about it. But the good thing is once I'm confident that that's what J is, it also helps me work out what I is, because all I've done from I to J is just put the chlorine here, which means that I must be this, but instead of chlorine, something else. So I'm going to go in and draw that as well. I'm not going to draw all of it. I'm just going to draw in that, and then I know that there has to be something else here. Okay, that's not a methyl group. That's a blank space for me to write something else in later that I've replaced it with. And if I look back, I can get some clues. So I start with this. I've got my one nitrogen here, and that nitrogen ends up here. And then all I've got is carbons, hydrogens, and oxygens. And all I do is a reflux, a sodium hydroxide, and another reflux. So this group here is going to have only carbon, hydrogen, and oxygen in it. Which means there's not much it can be. It's either going to be an alcohol or an ester. You know, it's probably going to have to be an oxygen bonded here for it to be replaced by the chlorine. All right, so let's not worry about it for now. Let's go back. Okay, so there's two other things that we can think of. So when I see this minus CO2, that says to me decarboxylation. So what that means is I'm going to have an acid, and I'm going to end up with nothing. Okay, so I'm just going to remove the carboxylic acid group. Yeah, carbon and 2 oxygens. So this step here, I'm thinking decarboxylation. Sodium hydroxide. Well, over here, what have I got? I mean, nothing happens to the chlorine. The amine is just going to become part of the ring. Here, what could my sodium hydroxide be doing? The only thing is going to be ester hydrolysis. Okay, so with these things in mind, and again, you know, once you've got ideas, sort of clues as to what it could be, you don't want to stay completely 100% attached to them, but it is a good idea just to have an idea of where this might be going. So I'm going to do my cyclization, I'm going to do an ester hydrolysis, I'm going to remove a carbon dioxide, and then I'm going to replace something with a chlorine. Okay, so now we can go back and we can look at the ring formation. Now the ring formation is a really good one because it's unlikely that your average A-level student is going to know much about ring formation reactions. But if you know what to do, it's actually quite straightforward. So all you need to do really is work out which two carbon atoms are reacting together. So if you look at your starting material and you look at your final product, you can see that it has to be a bond is forming between this carbon, obviously, and then I just count round from my nitrogen. So I've got nitrogen, and I've got 1, 2, 3 carbons. So then I go 1, 2, and then I've got 2 options, but it's symmetrical, right? This side is the same as this side, so it has to be between these 2 carbons, let's say. Okay. All right. So let's do that. Let's bond from here over to here. Now, what that's going to do is it's going to break the ester off. Okay. Which is going to be quite nice because then what's going to happen is if the ring formation gets rid of this ester, then this step will get rid of this ester, change that down to the carboxylic acid, and then the decarboxylation will take care of that completely. Okay, so let's try and write down what G is. So G is going to be so there's the N, and then I'm not doing anything to this double bond, so I'm going to keep that double bond as it is, like that. And then this carbon, again, really important to keep track of the carbons, is this carbon. So then I'm going to come down to here, and then this carbon is this carbon, so then I've got my carbonyl there, and then I need to work out where this bit goes, okay, and that's on the second carbon away from the nitrogen, so I go 1, 2, so it's on this carbon here, so that's going to be like that, and it's an ester, and I need a hydrogen there. Okay. So, that's fine, and at this point now, it's just fairly straightforward, right? Because I said, didn't I have ester hydrolysis. So my ester hydrolysis is going to convert this down to a carboxylic acid. So I get, fit it all on. Like that. Then I get my decarboxylation, which is going to break off this. And if I break that off, I get I. So let's draw that out, because if you've managed to stay with me this far, you'll realise that there's a problem. Okay, so it's like that. Okay. Now, I've done it through to here, like this, and that would be acceptable. Okay. But you'll see that there is a rearrangement, okay, from the double bond here and the double bond here to 2 double bonds in the ring. So what that is because of is because, let me just put that hydrogen there, these two are both acceptable. So this is another, this is like a keto-enol tautomerization. Okay, so what I can do is I can sort of bring the electrons down here, put that double bond there, put this onto here, or to give me my H hydrogen up onto there. But the point is that these two are both okay. For me, that's the hardest part of this question, is I would get to here and I would think, oh no, this doesn't look anything like what I wanted it to be down here. And I think seeing that rearrangement is quite difficult. I mean, in the mark scheme, they will accept. They'll accept either one up here. They'll also accept either one here. So you could have drawn it. You could have drawn it with the alcohol here and the double bond there and the double bond there, and no hydrogen there. But yeah. So like I said, it's unlikely that you're going to know this reaction. And when I go through the question, I try as much as possible to go through it in a way that you can see that it is perhaps somewhat possible to work out what it is without knowing the reaction ahead of time. And that's what they want, right? The people that write these questions, they want you to be able to work through without knowing it ahead of time. And it's by applying your chemical knowledge. Ironically, the best way to improve your chemical knowledge is by studying as many reactions as possible. So, you know, if you're looking at getting these questions right, the more reaction mechanisms and reaction examples you can study, the better, because then you sort of know the only way that you can sort of make this link between sodium hydroxide and ester hydrolysis is by just having a feel for, well, I know I've got esters, I know I've got sodium hydroxide, it's probably going to be an ester hydrolysis. So the more reactions you study, the more likely you are to be able to do that. One thing I will say is that in the mark scheme, they do have a lot of no ECF, no ECF, no ECF. They don't state it here. They usually do state it, but the implication from no ECF in a synthetic route is usually that you could reasonably work it out backwards. So you might think, oh well, look. So here, you might think, well, what if I didn't have? Let me think. What if I didn't have the double bond here? Could I get some ECF marks? And the reason you can't is because there's a double bond in the final product, right? So there is this understanding that generally when you look at these kinds of questions, you should be looking at it definitely forwards and definitely backwards, working backwards as much as possible. So that's why they're very reluctant to give ECF in a lot of these cases. But yeah, I feel like really nice progression in that question. That a lot of the earlier marks were definitely achievable. You know, so this was all fairly straightforward, and then it just got a little bit more complicated, and then it got really tricky towards the end, but definitely within reach.